Okay, everyone. Welcome to the Oracle Machine Learning Office Hours. This is the Oracle Machine Learning for Spark session. My name is Marcos Arancibi. I'm Product Manager of Data Science and Big Data. And Mark Hornick is joining us as well. He's the Senior Director of Product Management for Data Science and Machine Learning. And we also have some of our developers that will answer any questions on the Q&A session today. Vlad Shanarhovic and Dmitry Golovashin are going to be looking into the questions and hopefully answering any requests that come through. So the first topics we're going to talk about today then is upcoming sessions. We're going to also touch on the web questions, and then I'm going to be doing the session, and then we're going to go through Q&A. So the next session to look for on March 11th, 2020, we're going to have our Oracle Machine Learning Office Hours specifically doing a deep dive on Oracle Machine Learning notebooks, understanding better how to use it, looking into Zeppelin-based interfaces, the Oracle Machine Learning for SQL API functionality, some things like partition models and text mining. So Mark Hornick is going to be presenting, and I'll be joining as well on that session on March 11th. The web questions. So we got two questions. One was whether Oracle Machine Learning support creation of PMML-based models. So right now, we are not supporting the PMML specifically. We're looking from the different point of view on our new Oracle Machine Learning services. That component might have some functionality based on a more open source project. But for now, we are not really capable of exporting the algorithms, right, and the models themselves into PMML. We can normally score through, you could probably score algorithms, right, using the Oracle REST API services as well. So in that sense, that can be done.
Yeah. One thing to add to that, Marcus, is just that the PMML actually is supported for the regression model. So the data mining group, we have a PMML 3.1 version that can be imported for that, but that's the extent of it, just for the regression models.
Right, and just for the import.
Mm-hmm. Correct.
Thank you, Mark. Also, on the other question, whether the OML4Spark is going to be available with the new big data service. And the answer is yes, it's going to be made available. We are working on some scripts to get it installed on an edge node and on the big data service. The idea is that you probably don't want to install it directly on the nodes themselves. Because of the flexibility of big data service, the nodes might be small. So you might want to add it onto an edge node together with things like RStudio or components like the Apache Zeppelin, right, or the Jupyter Notebook, right? So that gives you flexibility on that portion. So for more product downloads and more information, we always tell you guys to connect to oracle.com/machine-learning. That is our main source of information. From there, you can jump into all the other components of the Oracle Machine Learning. There's always the always free services. So if you go to oracle.com/cloud/free, you always get a always free new service there. And then particularly in the autonomous side, you can always use that tier for running Oracle Machine Learning against the autonomous, right? The Oracle Machine Learning notebooks as well. So in today's session, I'll be basically talking about the machine learning for Spark. I'm going to be showing some demos as well. And basically, what's the idea behind it, right? Against data lakes, what's the kind of things that we can do that we can push to a cluster, right? And all of the integration that we bring. All right, so I'll start. So first things first, safe harbor statement. Then basically, I think pretty much across all of our components in the Oracle Machine Learning family, we try to get three things very important, right? The first thing is the automation. Try to to make things easier for the end user. The second part is to make sure that it's scalable, right? So that it can scale very well. And then the last thing is to make it production ready, right? Trying to make it in a way that you can actually reuse it and actually predict, the outcomes, right, coming from a model that you just developed. So that's our main job, our main objective. And in that sense, the Oracle data platform, right? If you look at the different data platform products that we have, so on the data management section, you see that you have autonomous data warehouse, autonomous transaction processing, right? You have big data service. So the idea is, for now, these are the components where our built-in Oracle machine learning algorithms are, right? So they are inside the autonomous data warehouse, the autonomous transaction processing, and in the big data service. We are working to get it running as well with the Spark data flow service, right? The OCI data flow as well. So having said that, right, the entire family is always getting a little bigger. You guys know from our previous session that OML4 Python is coming, right? Our Python API, and we're still working on the OML services as well. We're going to be adding some very interesting model management to that component. So that is coming in the future. In general, right, these are the components that we have for our platform. So you see on the left-hand side, we have the user interfaces, the API options, and that's the idea, right? The API options on premises and the data lake component as well. When you think about the Hadoop cluster, basically the idea is working from an R client, right? So the machine learning for Spark client libraries get installed into an R session and are running on an R environment, either on your client or typically on an edge node. And from there, what we're going to do is we're going to access the Hadoop cluster. We're going to go through Hive, we can go through Spark, we can go through Impala, and we can generate SQL and Hive SQL, right, or Hive query language, right, HQL, directly against some of the tables there where we're going to do basic statistics, right, data preparation, joins, and view creations, and things like that. From our R client as well, we can launch these Spark-based algorithms, right? We have OML4Spark algorithms that we built ourselves. So this is deep neural networks. We got GLM, LM, ELM, those so extreme learning machines, hybrid extreme learning machines, and then the single value decomposition, SVDs, and also PCA, principal component analysis. So on the Spark machine learning libraries that we offer an interface to, then we can also do their LM and GLM, lasso-rich regression, decision trees, random forest, SVM, k-means, PCA, and gradient boosted trees. There, then we're going to allow you to, if needed, right, compare the two results and look into that capability. We also have the ability to run R packages. So if you have an open source R package that you want to distribute the computation to a cluster, we allow you to do that. We use MapReduce for that, but we allow you to do that if that is needed, right? If you have a custom algorithm or custom package, right, from R that you want to use. From that point of view as well, we integrate with the Oracle database. So we can connect to the Oracle database through JDBC or through OCI native methods, and then we can bring in or write out data to an Oracle database from within your cluster. We use some of the other Oracle Big Data connectors components. We have the Oracle Loader for Hadoop, for example, so we can take advantage of that ability, right? Versus using Scoop, but otherwise, if that is not available on your cluster, we can use Scoop as well as a method to exchange data with an Oracle database. So I think that's pretty much gives an idea of that. On the specifically on the R language, right? On the components from the R language, the idea here is you can from both from R and from a Java API standpoint, you have abilities. You can basically bring in all the powerful, Spark processing that we have, and that you can use across several of the data lake sources. You can also achieve scalability and performance because we're using your entire Hadoop cluster. We're taking advantage of all those computational nodes. The machine learning algorithms are all parallel and distributed. So as long as, of course, you have enough data, you can distribute that computation across many, many nodes. And basically, we allow you to use the expressive R formula to specify your target and your input variables. As a function of these APIs that we offer, we have a transparency layer. So on top of proxy objects, you actually are able to use R basic components and language, statistics and tables and aggregations directly against some of these components like HIVE or Impala or Spark DataFrame. And we overload some R functions, so they are going to be basically native for you. And you can manipulate data using the standard R syntax. So I'll show you guys in a demo that I have. Also, the algorithms, as I mentioned before, these are going to be all distributed, and then you're going to be able to use these R mappers and reducers as well. In general, when we're thinking about the abilities of OML4Spark, I like to use these types of examples, right? So what happens is if you have a certain amount of data, if you have a lot of data and you want to try to play with these data sets, the OML4Spark is going to outperform the same algorithm running the Spark machine learning library. So a Spark MLlib, which are the open source components that come with Spark, right, and are available there, they are great algorithms, and we offer interface to them, but were not made for a gigantic scale. So depending on how large your data is compared to the memory that you can assign to a Spark, it's just not going to be able to run. In this example here, both environments are running until 1 billion records. Now note that this is a log scale, right? So this is we're around 7 times faster than Spark MLlib. But then at a 10 billion records, the MLlib just would not run, right? It will give you an out-of-memory error. And that's because the way that the algorithm was written, it requires the entire data set to fit in memory, but not only the entire data set, right? The matrix, when it inverts the entire matrix, it's got to fit in memory. And those are the things that we have, our patents that allow us to do that in a very efficient way, and we never run out of memory on that way. In any case, I'll leave you these slides, and I'll have the formula down here if you guys want to play with that and try to run it. This is using the on-time data set that is a famous the airline data set, right, for flights landing on time. So it is a very commonly used data set. You guys can see if you can scale, and you can test it out. Spark also has a Spark R language, right, that comes with it. And there are a few interfaces there, but some of the things that they have not done so is the creation of these more complex formula. So when you have a formula, for example, on a GLM where I want to do age plus number, right, to the square here, which I want to distribute this formula, right, and I want to do that interaction of the two columns together, it just doesn't work, right? So the normally in Spark R is not going to let you. It's going to just give you an error. So what we have done is we have created the formula parser that actually handles that for you. So even if you're using the open source Spark MLlib logistic regression, it's okay, because we are now processing that formula for you. We then create the appropriate label point RDD required, right, for processing that, and then we execute that logistic regression with that new formula. So when you get the output, you get actually the correct coefficients And the last coefficient here is the one related to that interaction, which previously Spark R was unable to do, right? And just to show you the coefficients are the right ones, I ran the open source version here, and you see the numbers, right? They are exactly the same. Also, on a different twist as well, when we think about Python, right? And OML4Spark, this is not really nothing against Python. We are actually going to go and produce a Python interface for OML4Spark, right? That's our next big project. Now, on the other hand, we think that we can make it easier for the end user, right? So on the left-hand side, you see what is today, if a user that is running Python and PySpark wants to do a random forest against a Hive table, right? So there are many things that have to happen, and the basic Python user has to do. And at the end of the entire process on the left, you see that you end up with a third copy, right? You end up with 3 copies of the data, because you need to pull it from the Hive, and then when you do that, then you have to split it up, and then you have to start creating. So the problem there is there's not a lot of efficiency, right? You end up, you can do it, but you end up with a complex process. So on the right-hand side, you see the same model, the same comparison. I actually spend many of those lines, right? There's 14 lines of code, just connecting, right? Calling my libraries, connecting to Hive, creating my Spark session, and then is a one-liner, build a random forest model, and I pass the formula, what's my target and what are my inputs. And then I predict with a one-liner as well. So we want to bring that kind of easy of use also to Python. That's going to be our next, one of our next components to build. So having said that, I'm going to go to a demo, and please continue, asking questions, and feel free to do that. So I'll bring up my my components here, and what I first I'm going to show you guys is the kinds of interfaces, right, that you would expect with OML4Spark. So first things first, I think probably 100% of my customers use Spark and OML4Spark, and all of them, when they run these things and they run from R, then they would use RStudio, right? So RStudio is a tool that will work well, right? And it works. In this case, I'm doing a VPN into one of my servers. I'm doing a forwarding a port here on a local port, but it's a great tool. It's definitely very open. You can do a lot of these components and a lot of flexibility, right, with that. Now, the only challenge for this session is the comments, right? So anytime I'm doing some comments, it's not going to look big enough for you guys to look at. So what I did is I took all of these demos and I built them into Zeppelin, right? Apache Zeppelin. And the Apache Zeppelin interface is going to be available for Big Data Service. It's an open source project. You can make it available for any of the other components. You can run it yourself on many interfaces and edge nodes and things like that. So I will show you this interface instead, and then anytime, everything that I'm doing here is completely available in any R session, including a terminal, right? So this is not exclusive from a Zeppelin interface, right? This just makes it easier. So so I have basically an initial basic HDFS tutorial, and I'm going to skip through this because this is less interesting. But in terms of how to work with the environment, right? So the first thing, I'm going to connect to the environment. I can then list all my content in HDFS, right? So I have functions in R that are going to list my content in R in the HDFS, what is in my folder. I can push a data frame from R directly into Hadoop, right, in HDFS. And then I can visualize that data. So I have functions that will allow me to take a look at the results, for example, from a function called describe, which shows me what is in that data, right? So I can see table name, the names of the columns, the types, the data frame, what is the a comment here from the origin of that file, right, and things along those lines. So another function that I can do is I can check the types of the columns, right? So it's numeric, and there's a factor. I can visualize the data in this environment as well, right? So I can pull in that directly from HDFS, right? I can pull that into Zeppelin's memory and illustrate and show that directly here. And I can create a permanent storage as well, because what happens is when you push that for the first time, it is always temporary, right? So for creating a permanent storage, then we'll give it a name. So we'll give it a DFS name so that is going to get assigned inside HDFS into a specific folder. So once you do that, you have a permanent location assigned to it, right? And then I can check the permanent file the same way I was doing before. I can also pull that file, right, with HDFS get. So say another user wrote an output, right, of my data and my processing, and they wrote it into HDFS. I can now pull that into locally. And for example, I can do a chart, right? So I can create, play with just as many, open source tools and libraries, right, that I would like to. I can use that same library right here. I'm just pulling that data over the wire. Now, of course, you got to be conscious that you're doing that, right? At this point, the data is coming over into my R's memory, right? So you don't want to pull 100 million records. You can pull samples, for example, of that data, and that will work, right? So having said that, I think more interesting nowadays, right, is the second section here, where what we're doing here is we're getting started with HIVE, Impala, and Spark DataFrames. So after connecting to HIVE, I'm going to push DataFrames to HIVE, check the statistics and aggregation functions, and then do a subsetting. And after I do that, I'll do the same thing with Impala. And then I'll connect to Spark and manipulate HIVE tables via Spark SQL. And then play with the Spark data frames. So at that time, it's the same thing. I'm going to go with statistics and aggregations and subsets of those Spark data frames. So for connecting to HIVE is very simple. Basically, I'll leave the instructions here. So I'll share with you guys this notebook. So it's going to be easy for you to see. You can copy this code. You can take a look at these. There are other options and other things that you might need to set up in terms of security for HIVE. But then basically the idea here is that we can list the tables that are connected. So this is using the transparency layer listing. I can check the tables in HIVE available to me. And what I'm going to do is I'm going to create a simulated data here, 100,000 records, 26 columns. And I'm going to push that to HIVE. So I use the HDFS put. I put it into HDFS first with a permanent name. And then I use my function HDFS to HIVE. There are some warnings because sometimes HIVE cannot handle specific column names, right? So HIVE is going to be changing that for us. And then now I see that my new table is here, right? I got my new table, simul table that was pushed and populated there. So I can take a look at that table. And now the thing here is I'm looking at a sample of that table from HIVE directly, right? The default here is 1,000 records. I can add more if I wanted to look at more. But remember, this is a 100,000 record table, right? So I don't want to pull 100,000 records to my Zeppelin session, right, in my browser. So 1,000 sample is fine. And then I can then look at creating new columns. So for creating new columns, I create a new table. This is a temporary table. And now I added new columns that are a combination of other columns. And I'm plainly using R. This is just R language, right? One plus the other times the other divided by that. It's simply R language. But the interesting thing now is I have these new columns created on this temporary HIVE table, right? So I see my new columns there, new HIVE variable 1 and 2. And I can check, I can count and check how long it takes for me to count the new table. It still has 100,000 records, right? But now I can push that. So I can, if the original simul table extra exists, I can drop it. And I can create and push from the temporary table. I am now writing a permanent table in Hive, right? So now I can do aggregations and functions. We created an orch.summary function. This allows you to request statistics like minimum, mean, maximum, standard deviation, and many other statistics. So you can check for the help of the orch summary component that we have. And these are the statistics for all the columns, right, that are ordered. I requested for V2, V3, V4, and V5, right? And I asked for a class new hire var1. So now it's going to do the whole data set, and then it's going to split up between 1 and 0s so that I can see what are the different minimums and different maximum and things like that. Other functions that we can use is aggregate. So aggregate is a plain R function. This is a straight out R function, and I'm using it against a Hive table. And at that point, I'm just executing that, and Hive understands that and creates the query behind the scenes. So I'm not pulling data to R's memory, right? I'm running this aggregation as a query that I'm pushing to Hive. So now I can get that result. I can add a new additional factor, so I can get 2 factors here. I can use the table function, right, also transparently. And that table function is going to give me this cross-tabulation format. And I also can use other transparency functions like column means on top of Hive, and I get all the column means from the entire data set. So it is a very easy way for us to pass information to Hive, and I did not have to write SQL at this point, right? I'm just writing R, plain R language. Now, I can subset also Hive tables using, again, R's own subset. With that, I can basically subset this, and I'm saying I want to select only these columns, right, on that data set. And now when I do a head on that view, now this new view, which is created by this subset, only has the columns that I requested. And I can, again, same as before, I can pull all the data locally and then run, say, a standard R summary, for example, on it, right? So switching to Impala now, right? You can, the same kind of connectivity, right? I, again, put the usual ports. You're going to have to find the port that you're using for Impala on your Impala daemons on the cluster. But usually it's the same kind of connectivity where you're going to use the same command or reconnect. And at that point, instead of mapping all of the tables like I did with Hive, I'm going to just do a synchronization on one table, simul table. So when I do ls, I'll only look at that. So these are all options you have, right? If you put through here, you're going to see all the tables again, right? Now I can push table and data to Impala as well. So I'm creating my simulated data again. I'm dropping that table, and I'm checking the size of my table, and then I'm doing ORE create now. This guy pushes a standard R data frame to Impala, and then that's the name of the table that's going to write it. So again, verifying the data that is there, right, should be identical to the data that we pushed when we did it with Hive. I can, the same thing again, create a new temporary table, create new columns, and check the new columns are here on my output, right, as new Impala var in this case, 1 and 2. I can do a count, right? The counts here in Impala are substantially faster than the counts in Hive, right? When Hive does it through MapReduce, for example, then it will take around 30 seconds. With Impala, it's always 0 point something seconds, right? In this case for that table. But again, statistics and all the aggregation functions apply. So you can use open source R aggregate, the same way of calling that information, a bigger aggregate with more, using transparency layer with table, same thing again works. And the column means again, right? Also subset works, so the same subset you can do as we did before, the same kind of only 6 columns that we get. And if I bring it locally and do an ORE pull, you can do things like, histograms or whatever you want to do locally again. Okay. Now, Spark has a very interesting relationship with the Hive metadata, right? So nowadays, Spark can look into the metadata from Hive directly. So what happens here is, now I'm going to do a Spark Connect, but I'm going to say enable Hive equals true. With that, what I'm doing, and I'm telling Spark, is I'm telling it, hey, please connect to the Hive metadata store and let me take a look at the tables there. So things like show databases, right, will work directly here. So I can take a look at the database names, for example, available for me, right? I can do show tables, right? So doing the show tables, I can do this query, and I can then see the database and the table name, right? So I can see all these table names, and you can see even the Impala tables, right? So both the Hive and Impala tables are going to be showing up here, but they are being queried by Spark in this case, right? So I can do things like now push SQL, right? So now I can do Spark SQL queries using my ORCHDF.SQL function. So I can do a select count star from a table, and it's going to be shown back here, right? So now that I can play with that, I have also a special function to query these things, and I can play with more select count tables, right? Check the number of rows via Spark SQL, and I can load the Hive table into Sparks. So what happens here is, with this function, I'm taking this table from Hive and I'm loading it into a Spark as a Spark data frame. So once I do that, I can see that my simul table df is now a Spark data frame, right? So it's a part of an R Java package, so it's a job Java reference, right? And I can see, the structure of it. It's basically that class, and you can see it's an Spark data set, right? So it's part of that Spark data frames family. So it's a Spark data set that I created. Now I can visualize it, and I can, for example, do things like I can persist that Spark data frame. So I'm telling Spark here, hey, I want to do a lot of aggregations and tests on top of this. So why don't you go and pin this in memory? Because after a certain time, Spark might opt to, push anything out of memory, right, and just keep the latest and greatest queries that you're running. But you might say, I'm going to use this table all the time, so I want to pin it in memory, to memory only, please. And as long as you have enough memory, right, Spark is going to do that. If it doesn't, Spark is going to spill into disk, but don't worry about it. It manages that. So at this point, you get again, count. So functions like count would work directly against that object. And statistical and aggregation functions. So Spark has special functions like only check the numeric columns. It has functions that are things like stats functions. So with that stats function, it actually can create correlations. So you can actually run a correlation function, like a dollar correlation function, on top of the stats functions object. And then you can see what are the correlations between all the variables against V2, for example, right? That's what I requested here. So when you do that, then you get, of course, the correlation between the variable and itself is 1, right? But then you get an idea of what's the correlation between that variable and all the others at once, in a very simple and fast process, right? This is going to run very, very fast in Spark. Other things that are available for you are the cross tabulations. So the same thing again under that object that simulated that stats object. Cross tab can be used directly in R. So again, I'm just writing R functions and running these R functions against my Spark data frame object, and then I'm creating this cross tabulations there. Subset as well works well in terms of selecting, specific columns I want to use, and I can see the output here. Or I can basically do a subset on a query. So now that I can send a ship and a specifically Spark SQL query to the cluster, I can just do my select from here. And I can do a where, and I can do whatever I want, right? I can combine Spark data frames as well. There's a very easy function union that I can use, so I can stack the columns, and I can see that if I do that, I am stacking a subset table on top of a subset query, they still have the same columns, but now when I count, they have 200,000 records available. So finally, for joining Spark tables, right? Again, I can show the tables. I can see that one of the tables is not here, right? So the subset query data frame that I created is not available here. So what I need to do is I need to create a view with that. So this is a temporary Spark data frame or data set. I create a view now with a specific name. So when I do the same query, if I scroll all the way down to my list of tables here, I see that now that table is available for my query environment, right? Even though it's temporary, right? Because it doesn't have a database, but it is registered as a subset query for me. So with that, I can actually run a SQL query and a SQL join. So this is basically the way I'm doing this join, right? And you can do that join directly from these two tables, right? From the simul table that is a standard registered table there with the subset query that I just created, right? That is a temporary data frame. So when you do that, then you can bring the data locally, right? So I'm bringing it locally into my memory, and then I'm doing a histogram with it. So that's basically the idea. So you have a processing of things like Spark, Spark DataFrame, HIVE, Impala, and all these other components available to you. Now, another example that I like to show is something like this one, which is basically I'm looking into, in this case, as a very simple example of the bikes, right? And the bikes riding in New York City. There's a data set that is available there, and you can play with it. And basically, the idea here was, okay, I will take a look at loading that CSV file, right, from HDFS into my Spark memory, and using Spark SQL to create attributes, and then determine the appropriate model, right, to try to predict this demand, right, of the stations. So the bike stations, right, there are people coming and going every day, taking bikes and putting bikes back, and I want to take a look at that demand. So again, connecting to my, bringing my library, connecting to Spark. Now I'm loading that data, and I'm using one of these new functions from CSV, and this function is going to bring data from HDFS in a CSV format, right? And it's going to bring it into memory. So I'm just showing how many records there are, right? I'm just pasting this thing here. So you see I have 1.2 million records here available, right? I'm showing you the records, right? Just a sample of the data, how the data is distributed, the reported days, number of bikes available, and things like that, right? Weekday and things along those lines. So what I'm going to do here is I'm going to transform columns, right, directly. So remember, I need to create a view. So I'm creating a view of that station. I'm calling it a temp view. And then I'm running SQL and Spark SQL on top of it. So I'm creating here some things like substring of the last reported time, right? Because I'm trying to add this thing. So I'm getting this components multiplied by 60, substring of the interval starts, right? Because the data was coming to me with hours, right? And like that, right? Hours, and that's not going to help me here. So then I'm picking up the data, the hours and minutes, and then I'm checking how long it's going to take, right? So again, I can look at my final data set, right? This is my final data set with my times all in seconds, so I can compare. And then I'm using now a split function, so I'm going to split. Usually data scientists would like to split their data into testing and training, right? So again, we have a random split as list function here that we can use directly on top of our object. So on top of our Spark data frame, I'm splitting that. I'll do 60-40, and I get my training and I get my test, and I'm going to show you the training count. So I have that many counts for training, that many for testing, right? So I have now two Spark data frames that are separate, right? That's called training, and the other one is called test, right? Now I can build, for example, several different regression models, right? So this is a the brute force way of doing it. So if, say, you wanted to do many models and want to test them all, I can brute force this, right? And I can do something like that. So I can say, you know, I start with a formula that has many variables, and every step I reduce one of the columns, right? And I take one of these variables out, and then start seeing whether that's going to make any difference, right? So it's a way of doing it. And I'll show you guys next an example where that's probably better suited for it. But once you do that, because I'm doing that, I'm accumulating the models in as a list in R, right? So now I can get a model stats function, and I can get things like, because I'm using the LM2, right? The OML4Spark's linear models directly. I have things like statistics like summary. I have R squared. I have RSS, and I got the coefficients as well, right? So I can check how many coefficients I used, right? So I can check things like that, and I can run that process. I do that as DataFrame, so then I can bring it locally, and then I can finally take a look at that. So I check model quality, right? And I can see, you know, number of coefficients that I needed to compute, and compare that RSS and R squared. So that is one interesting way to see that. And if I say, okay, now show me one of the models, right? Model number 3, for example. I can check the output of that model, and I can see all of the coefficients for each of the stations, right? So each of the stations here are considered to be different, slightly different, right? So they'll have their different estimates, for example, in this case. Now, once I do that, I can run predictions. So if I say select that model as my best, I can then take the test data, right? And I can, again, adjust that test data to get only the variables I'm interested in, and I can run a prediction through it. So I can predict my model doc demand, right? And that was my model, the third model, using the station test as my output, or my input, right? My input test data. And these are the supplemental columns that I would like to have, right? These are all things that are normally not done in the prediction side, right? If you look at Python, you probably have to, after the fact, join data and columns to the predict output, which to me doesn't make a lot of sense. So to me, as a data scientist, I want to see my output and my predictions, right, together as a one good set of records, right? So then I have the station ID, and then I have my all of that data, and then I have my predictions, right? So that's somewhere what I would like to look at. So and that's it. So then at the end of the day, you can get some specific listings for predictions, right? For the station ID, if it's Sunday, right? Depending on the weekday, this is the prediction for that. Depending on the day, right? This is a Monday. So that's basically what you can do with this process, right? And at the end, you can disconnect and terminate that, clean up that process. Now, this is a brute force way, right? Approach for that, and I was using only one of the models, right? So I also wrote some basic helper functions to give you an idea of playing with the data. So trying to get a better output. So I'm using here, I said I was going to use all state, but I'm actually using the on-time data set, because I can't use this one. This other one is from Kaggle, so I can't distribute that to you guys, but I can distribute the on-time data set or point you guys to it. So I'm going to rename that to on-time everything. So I'm using the on-time here. And I can check, for example, I had an on-time 1 million records in Impala that was available to me. I loaded these functions that I'm going to show you later, and I am created a balanced data frame. So, for example, I started with 10,000 records. At this point, I wanted to get 10,000 records out of that million records. So originally, that million records had only 18,451 canceled flights, right? Thank God, right? And then 981,000 flights that did not cancel. So now what we're doing here with this balanced input is okay, I would like to balance out my input. So I want to take a sample of my target equals 0, and I want to equalize that, right? So I'm going to get 18,000 from each. But because I requested 10,000 sample at the end, it's going to be sampling down the final 36,000 records down to 10,000, and it gives me that into that data frame. So with that, I can check out the cancellation levels, right, on my sample, just to have an idea. I think 2 might be Tuesday or Monday and Tuesday, highest cancellation days. But anyway, and then I'm calling the special function that I created for the cross-validation. And what this guy is doing is taking that original data set and using it cross-validation with k-folds to select the best model for you. Because I might not know, or I want to just have a first pass, then what it's going to do is going to split those into different k-folds, right? So these similar amount of records, and then it's going to run cross-validation. So it's running all of the algorithms that we have. So it's going to run GLM2 for classification, right? Neural networks with entropy, neural networks with softmax, the extreme learning machines, the hybrid learning machines, and the Spark MLlib as well, logistic, decision trees, random forest, SVM. So it's going to run for each of the cross-validations. And at that point, it's going to be able to show me what is the best model, right, based on the statistics I requested. So based on the statistic I requested, it looks up here that is the random forest, right? For some reason, random forest is better for solving this specific problem. Then you got SVM, you got GLM2, you got the Spark MLlib logistic. After that, you got neural nets. So you can also sort, right? Because this is the Zeppelin interface. You can sort models, by hand here and see which one is the better precision, or area under the curve, or things along those lines. So many of these statistics are related, but sometimes you're looking for the true positive rate or something like that. So it might be a different one that jumps up, right? So that's just to give you an idea. And my suggestion is, okay, now that you have that, you can take a look at the model and then build another model. Right now that you know that this model is better at this, for example, true positives that you're looking for, then you might actually investigate the two first, right, the 2 or the 3 top models, and you don't have to worry about the rest. So that was a great quick overview of that. Now we're gonna get to the top of the hour. I just wanted to show you one more thing real quick. These are some of the benchmarks I did for 100 million records. So when we think about just the art of the possible, right, is taking that on time 100 million records and showing you how I'm doing this. So I'm just picking it up from HDFS. I have 100 million record CSV file there. And then I'm running it, doing a formula that actually have enough coefficients, right, that I'm going to generate. I take the Spark context and I execute my model and I predict it, and this is the final result, right? So I get the 100 million records, 9,000 coefficients. The build time was 93 seconds. The scoring time was 19 seconds for those 100 million records, okay? And this is the code that I used, just so you know. So I'm not cheating. I'm just literally printing the dimensions of the data sets, and then the number of coefficients, and the build time, right, and the time for prediction, right? These are the data sets that were created out of that the build here, right? The system time of that build and the system time of the prediction. So anyway, I think there are many interesting examples. I hope you guys like this. I will share this code with you guys. What is coming up for our future, right, that we expect? There are a few things. The Oracle Machine Learning Services are coming up. It is already available for some internal teams to work on. But we're going to add the model building and monitoring services. So OML4Spark models are going to be part of that process as well. We are working on developing this new interface. We got new algorithms coming. But mostly we're going to be working on the new Python interface to this, right? It was overwhelming the amount of customers that ask for Python support. So that's something that we're going to focus on. GPUs as well are in our future. We're still working on that process, but I think Python is going to be our priority for now. As we mentioned, that's our idea for all machine learning for Spark. We have a specific link there, but you guys can always get to our link directly. One more thing is next week in Santa Clara, we have our Analytics and Data Summit 2020. So we have many hands-on labs there with the instructors, with product management. I think it's a great opportunity if you guys can make it. We're going to be all there, all the product managers for machine learning, the team on data science side. Everyone is going to be there and showing all of the best of the products. So with that, I would like to thank you for your participation and opening for any audio questions if the questions have not already been replied to.
Well, thank you, Marcus. That was a great presentation. Yeah, there are a few questions that we have in the Q&A there. One had to do with the cluster configuration used for the benchmark you just showed.
Oh, okay. Let me go straight to that. This is basically what we had. That was a big data appliance X7 with 6 nodes, 256 gigs of RAM per node, right? But of course, all of that memory is not used. Only when you need 10 billion records, right? The data set is when you hit that much. But before that, you don't really need that much memory, right? So in any case, we used a dynamic, so the Spark with dynamic allocation. So what happens is Spark and Yarn actually gives Spark only whatever it needs. So if I'm running 100K records, I might get just one container because that's all I need to solve the problem.
Great. And another question had to do with the relationship of OML4Spark with OCI data flow. Is there anything we can say on that?
Oh, yes. So OCI data flow, it is a Spark as a service component, right? So we are working on an integration point for that. Because the Spark data flows Spark sessions are only alive for the period of time where the processing is happening, then you would need to run, let's say, call the OML4Spark libraries and execute the code, right? And then the code is going to finish. So you're not going to have, let's say, like I was showing before, the Spark DataFrames where you can, keep thinking about what to do with it, let's say, right? So you would have, say, a batch job to run where you're crunching numbers, and then at the end of that crunch, you get either a model, our binary object model, right, from OML4Spark, or you get the output or a summary or results, right? But that's the difference between the data flow.
One other question came that is interested in comparing OML4Spark against Spark R, and that would you eventually achieve the same result using Spark R API as well? What would drive somebody to switch from one to the other?
Right. So Spark R has some things, has some features for sure. They have been increasing in terms of the amount of algorithms they can give you access to. But as all the open source projects are, I would argue, there are a few things in the algorithms themselves, right, that are not as performing or as good to use as the OML4Spark ones. So the idea is, I mean, if you're connected to big data service, right, if you're using our cloud services, if you have, the big data connectors on premise, right, on a big data appliance, all of these things are there for you. So you don't really need, I mean, it's not really a question of a choice. You can use both, actually, without much problems. The difference is going to be always in the algorithm and the capability on the formula, for example, support, right, that I was mentioning before. and the data preparation that a Spark R might require, right? So the data itself requires some preparations that we actually take care of that for you. But it's not a bad component, and actually I use Spark R underneath in Zeppelin, right? Because Zeppelin actually uses that to give us access to R on notebooks. So.
And one other question that came in, how does OML4Spark leverage Oracle Big Data SQL?
So Big Data SQL, right now we are not really leveraging Big Data SQL. Big Data SQL is an engine that will actually leverage a cluster to run queries, right, directly. But it's going to run, at its heart, it's going to run Oracle SQL against Hadoop and against HDFS and against Spark or against, sorry, not Spark, but against Hive, right, and Impala tables and things like that. So what OML4Spark does is it actually pushes the computation to the cluster, but the results come back, and you can store them and you can play with them. Now, the result of an OML4Spark computation, if I store it in Hive, for example, right? If I store my predictions in Hive, then Big Data SQL can actually query that table, right? So Big Data SQL could eventually pick up the results of any of the computations that I do with OML4Spark. But they're not like tied by the hip, for example. There's not specific communication between them.
Right. I think that's all that we have for questions in the queue. If there are no questions in real time, then we can adjourn. So again, Marcus, thank you very much for an excellent presentation, and we look forward to seeing everyone next month.
Excellent. Thank you very much. Thanks, everyone.